Welcome to Yatim Khana and Madrasa Anjuman Khairul Islam's Pune College of Art, Science and Commerce Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. So today we are going to study the topic which is called as anti-log amplifier using transdiode and operational amplifier. So the name of topic is anti-log amplifier using transdiode and operational amplifier. So in the previous lecture we have studied about a transdiode. Transdiode means diode fabricated by using transistor. Diode fabricated by using transistor. In anti-log amplifier, remember, we are going to use PNP transistor. In anti-log amplifier, we are going to use PNP transistor. In log amplifier, by using transdiode, we have used NPN transistor, and this is the difference. Now, why that difference is there, that you will understand slowly in this topic. So look at the diagram. We have taken PNP transistor. So in case of PNP transistor, all of you know that P-type semiconductor material, N-type semiconductor material, and again P-type semiconductor material. So it is said that in PNP transistor, N-type semiconductor material is sandwiched. N-type semiconductor material is sandwiched between two P-type semiconductor material. And therefore, in this transistor also, there are two junctions, namely junction J1 and junction J2, and both junctions are PN junctions. Only the difference is the sandwiched layer is N-type material. Now we want to convert this PNP transistor into a PN junction diode. We want to convert this PNP transistor into a PN junction diode such that on the left hand side we want anode, that is P-type material, and on the right hand side we want cathode, that is N-type material. So PN. So P-type material is anode and N-type material is cathode. So that's why we are using here a PNP transistor, because on left hand side we want anode, that is a P-type material, and on right hand side we want cathode. So in this case also, base is connected directly to the real ground. Base is connected directly to the real ground, and collector of transistor is connected to virtual ground. VG means virtual ground. And therefore what happens? The collector to base junction gets short circuited, means this N and P. Base is your N-type material, collector is P-type material. This junction gets short circuited, but one more junction is there, and that is nothing but junction between emitter and base, and that will work as a PN junction. Look at this. P-type material will be your emitter, N-type material will be base. So collector to base junction becomes short circuited, and that PN junction diode is disabled, and collector emitter to base junction and emitter to base junction gets enabled, and that PN junction diode is active, and that PN junction diode is active. And therefore here we want P-type material on the left hand side, that is your anode on the left hand side, N-type material on the right hand side, that is cathode. Therefore we are using PNP transistor. So one thing is common in case of log amplifier by using transdiode and anti-log using, the common thing is what? Always collector is connected to virtual ground. Always collector is connected to virtual ground, whether that transistor is a PNP transistor or whether that transistor is a NPN transistor. But remember, what is uncommon? Uncommon is in case of log amplifier. In case of log amplifier by using transdiode, we are using NPN transistor, and in case of anti-log amplifier using transdiode, transdiode means diode fabricated by using transistor, we are using PNP. Therefore, this configuration in which base is directly connected to real ground, collector is connected to virtual ground of the op-amp, that is point A, that you will come to know after some time, and therefore this will work as a PN junction diode such that left hand side is anode and right hand side is cathode. So we can show above this transistor only a diode, and that we are going to show in our circuit diagram. So this is basic understanding about the transdiode. And as you know, in case of anti-log amplifier, as you know, in case of anti-log amplifier, the diode as a log element comes first, and then in feedback there is a feedback resistor. So let us go to that diagram. So this is our circuit diagram for anti-log amplifier by using transdiode. Anti-log amplifier by using transdiode. So look at the circuit diagram. Circuit diagram is very important. If you draw the circuit diagram very carefully by indicating all notations, then derivation is very simple, because in derivation very basic laws are used, such as Kirchhoff's current law is used, potential difference logic is used, and then Ohm's law is used. So these three basic laws are used. But look at the diagram. The input voltage V in, which is to be converted into anti-log, which is to be converted into anti-log. So output will be the anti-log of input voltage V in. Output will be anti-log of input voltage V in. So input voltage, of course, DC, because in logarithmic amplifier, DC voltage is applied. And in this way here, the input voltage DC is connected to a transdiode, which I have just explained you. We have taken PNP transistor, and in PNP transistor, base is connected to the real ground. Real ground means dual power supply junction, and collector is connected to the point A, that is called virtual ground, because in op-amp whenever the feedback is done with the help of RF, the junction point of the input and feedback point voltage, that junction point is called virtual ground, and that is indicated by the symbol capital A, and voltage at that point A will be VA, and this virtual ground voltage is always 0 volt. Therefore now see here, collector comes to the virtual ground, and in this way collector comes to the virtual ground, base is directly grounded, so collector to base junction becomes short circuit, and emitter to base junction, this is emitter to base junction is active now, and therefore this emitter is what, your p-type material, base is what, n-type material. So in this way this will work as a PN junction diode, such that p-type material is anode, which is on left hand side, n-type material is a cathode, which is on right hand side, and this is what we want in anti-log amplifier. The diode should be here, whether it is a PN junction diode or whether it is a trans diode. The diode should be here, but anode of the diode should be on left hand side and cathode of the diode should be on right hand side. So the things are very simple. Now you can see here what we have written. We have written the voltage between emitter and base. Actually this terminal is collector, but why we have written here VEB? Because collector and base are short circuited, because base is directly connected to the real ground and collector is connected to virtual ground. Therefore collector and base are short circuited. Therefore we have written here VEB, emitter to base, VEB, because PN junction diode between emitter and base is active now, and therefore this voltage will be your VEB. So in this way you have to write all notifications, battery as a plus minus, trans diode you have to show only by connecting the base to the real ground, collector you connect to the point A, so it will be automatically connected to virtual ground. Now when you apply the V in, definitely current will flow, and that current will be emitter current, then it will go to the collector and that will appear as a collector current. And now here you see this collector current IC, which is approaching to the point A and coming to the point A. This IC we have written as IC is equal to ID. Why we have written IC is equal to ID? Because this entire transistor is working as PN junction. See here, the equivalent of that I have given over here. This entire transistor is working as PN junction, and therefore you can say that VEB is nothing but the voltage between anode and cathode of that PN junction. Therefore in the derivation we are again writing not only IC is equal to ID, but we also write VEB is equal to VD. VEB equal to VD means voltage across diode, because this entire device is behaving as a PN junction diode between emitter and base. So this you have to mark very carefully, VEB, IC, you write down IC is equal to ID. Here also you can write VEB equal to VD, come to the point A. Now incoming current IC, when it comes to the point A, it gets divided into two branches. One branch is called input current IB to the op amp, input current IB to the op amp, and another branch which is called feedback current IF, feedback current IF. But all of you know very well that input resistance of op amp is very high in mega ohm. Therefore, IB is very less. IB is very less. And I told you why it is IB, because inside op amp there is a transistor in the first stage, and this IB is the base current of that transistor. So here IB is very less. Therefore, it is said that this collector current, which is nothing but again a diode current, is 99.99% gets diverted to the feedback path. And therefore feedback current IF is very close to the incoming current IC or ID. So that we are going to derive in the equation. So in this way you have to write down these three notifications very clearly. IC you have to indicate, point A you have to indicate, IB you have to indicate, and then come to the RF. Then when you connect the RF in feedback, current IF will flow, that is called feedback current, through the resistor RF, and then it will come here. And here this is our output voltage. And in this way we have to follow from left hand side, go like this, and then don't enter into the op amp, then go to the feedback current IF and come to the output. So in this way we are going to derive the equation. Now here what logic we are using? We are using the logic of potential difference between 2 points, because whenever a voltage across any component is measured, we do connect voltmeter across that component. And suppose here now you want to measure the voltage between emitter and base of this transistor. Now base to collector junction is short circuited. Therefore, base to collector junction is short circuited. Therefore, this base terminal appears over here, and therefore it is written as a base. So here you connect the multimeter like that. So this multimeter, which is connected between this terminal and this terminal, will measure the potential difference between two terminals, which is on the left hand side and which is on the right hand side. Right hand side terminal is a terminal, which is called virtual ground, and that is VA. So this is a one right hand terminal voltage. Left hand terminal, if you look at, there is a Vin. Therefore VEB is equal to Vin minus VA. Vin minus VA. And then here when you come to the RF, voltage across RF, when you want to measure by voltmeter, then you connect voltmeter over here such that one terminal to the left hand side and one terminal to the right hand side. On right hand side there is a V out, on left hand side there is a VA. Therefore here voltage across feedback resistor will be, here the voltage across feedback resistor will be, right hand side voltage will get subtracted from left hand side. Therefore VRF is equal to VA minus V out. VRF is equal to VA minus V out. That is the way with which we can write the voltage across feedback resistor. And one more logic is there. We can define the voltage of this resistor by using Ohm's law. V is equal to I into R. You know the current flowing, you know the value of resistor. So VRF is equal to IF into RF. And in this way we'll proceed that derivation, which is very simple. And if you draw all these notifications very clearly, then you will not get any problem in deriving the derivation for anti-log amplifier by using transdiode and operational amplifier. So look at the diagram again very carefully. Remember the diagram, and whatever I have explained you this, that all things we are going to proceed slowly in the derivation. So let us see here. In above diagram, base is directly connected to real ground and collector is connected to virtual ground point A, where VA is equal to 0 volt. Therefore, collector to base junction is short circuited and emitter to base junction is active. So this, whatever it is written here, so it is here. Base is directly connected to the real ground. Collector is connected to the virtual ground, that is point VA. Therefore, this junction is short circuited and emitter to base junction is active. Next. Therefore, transistor is equivalent of PN junction diode. Therefore, transistor is equivalent of PN junction diode between emitter and base junction. That is called transdiode. Therefore, transistor is equivalent. This transistor is equivalent of PN junction between emitter and base. That's why anode comes to the left hand side, that is a P-type material. Cathode comes to the right hand side, and conduction takes place in this direction, left to right. Therefore, we apply V input voltage V into the anode. and then this is a transdiode. And then let us proceed for the derivation. Let us write the equation for VBE. Let us write the equation for voltage between emitter and base by applying the logic of potential difference. By applying the logic of potential difference between V in and VA. Because when you measure VEB, you connect one terminal here, which is left hand side V in. You connect another terminal here, which is right hand side A point, that is VA, and therefore it is very simple. VEB equal to V in minus VA. VEB is equal to V in minus VA. Right hand side voltage is subtracted from left hand side. So VB is equal to V in minus VA, and in this way, this will be our actually equation number 1. And then you'll know that your VA is a virtual ground point. VA is a virtual ground point. Therefore, VA is equal to 0 volt, and in this way, you'll get VEB equal to V in. VEB equal to V in. So equation number doesn't matter. You just remember that. This is our first equation say. In above diagram, VEB is the voltage across PN junction diode between emitter and base. Therefore, VEB is equal to VD. So that is what I told you in the beginning. Transdiode is equal to diode. VEB is nothing but voltage across diode between emitter and base. Therefore, VEB equal to VD and IC equal to ID. So that we are going to write in the form of equation. VEB equal to VD and IC equal to ID. Substitute equation number 7 in 6. Substitute equation number 7 in 6. What is equation 6? VEB is equal to V in, but VEB is equal to VD. Therefore, VD is equal to V in. VD is equal to V in. Simple mathematics is there. VD is equal to V in. Now, at once you complete this much portion here, you come to the point A. So very simple, you complete over here voltage across this, and then you come to the point A. As soon as you come to the point A, apply Kirchhoff's current law. What is Kirchhoff's current law? The algebraic sum of incoming current is equal to algebraic sum of outgoing current. Here there is only one incoming current, that is IC, and two outgoing current, namely IB and IF. IB is base current going to the op amp, which is very less. Therefore, we can write IC is equal to IF plus IB, but we will neglect IB, and therefore IC will be equal to IF, but IC is equal to ID, therefore ID equal to IF. That is what we are going to say in the statements here. So here VEB is equal to VD and IC is equal to ID. Substitute this equation, you will get VD is equal to V in. Now apply KCL at a point A. IC is equal to IB plus IF. Incoming current is IC, and two currents are outgoing, that is base current to the op amp and feedback current to the feedback resistor. But from equation number 7, IC is nothing but ID. Collector current is nothing but diode current, because transdiode is a diode. So here ID equal to IB plus IF. So IB is very low as compared to feedback current IF. Reason is what? Input resistance of op amp is very high. Therefore, small value of IB, which is very less as compared to IF, can be neglected in comparison with large value of feedback current IF. So IB is very small. Therefore, ID equal to IF. ID equal to IF, and this will be the equation number 9. Say here. So ID equal to IF. Now let us proceed next. Now at once you come here to this point, remember, over here. So you have applied everything and you come to the point A, and at the point A you applied the Kirchhoff's current law. Now after completing the Kirchhoff's current law, don't enter into op amp, follow the feedback path, and you come to the RF. Now here what you have to do? You have to express the voltage across RF by two logics. You have to express the voltage across RF by two logics. Now why we are going in this path? Because we want to calculate the output voltage derivation. So we want to go to output. So this, after this you come over here. So that is the way to remember. So now here KCL is over. So now let us write the equation for VRF. Let us write the equation for VRF by using the logic of potential difference between VA and Vout. By using the logic of potential difference. So let us see here. VRF. On left hand side there is a VA, on right hand side there is a Vout. So right hand side voltage is subtracted from left hand side. So here VRF is equal to VA minus Vout, but VA is equal to 0. But VA is equal to 0, therefore VRF is equal to minus Vout. This is the way with which you can write the voltage across feedback resistor by using the logic of potential difference. And there is one more logic, but by using Ohm's law, we can write V is equal to I into R. And by Ohm's law, we can define the VRF is equal to current flowing through RF, that is IF, and value of RF, that is RF. Now, what is your IF? Feedback current is nothing but diode current. Feedback current is nothing but diode current, and that is a collector current also. So instead of IF, we'll write down ID. Therefore, ID is equal to IF. ID is equal to IF because diode current is nothing but your feedback current. So VRF is equal to ID into RF. VRF is equal to ID into RF. Now what is the equation number 12? Voltage across feedback resistor by Ohm's law. And there is one more voltage across feedback resistor by using potential difference logic. So these two voltage represents the same thing. Therefore equating equation, that two equation, equating equation number 12 and 11, we can write Vout is equal to minus ID into RF. Vout is equal to minus ID into RF. Don't forget minus sign. Vout is equal to minus ID into RF. And in this way, you got succeeded to come to the Vout. That is what our target started from left hand side and we went to right hand side. And this is our target. So 90% job is done now. Vout is equal to minus ID into RF. Now all of you know that diode is a log element, and because of the junction capacitor of the diode, it works as a log element. And by using that equation of the diode current, in this equation, we can substitute that value. So using the diode current equation, and that equation we have studied from well beginning as a what? ID is equal to current flowing through the diode equal to IS, reverse saturation current, into e raised to VD, means voltage across diode, divided by eta, equality factor, into VT. VT is a thermal voltage. So this equation you have to remember. ID is equal to IS, which is reverse saturation current, into e raised to exponential e raised to VD divided by eta into VT. Now this value of ID substitute in this equation of Vout. So Vout is equal to, this RF will be as it is, minus sign will be as it is, only instead of ID we are going to write this IS into e raised to VD divided by eta into VT. Now solve this equation. In this equation, VD, what is the voltage across diode? Voltage across diode, in the beginning only we have derived that voltage across diode is nothing but V in. Voltage across diode is nothing but V in. From where you got that? How do you measure this voltage across diode? One terminal here, another terminal here. So V in minus VA. So VD is equal to V in minus VA, but VA is equal to 0. So see that equation here. So we got VEB is equal to V in, but VEB is equal to VD. VEB is equal to VD. Therefore, V in is equal to VD. Therefore, V in is equal to VD. This is equation number 8, you can say. V in is equal to VD. Therefore, in that equation, in the exponential term, what we can do here, we have written this equation, Vout is equal to minus RF, by substituting the value of ID in this equation of Vout is equal to minus ID RF. When we wrote this equation, we observed that VD is equal to V in, and therefore we have written this equation, VD is equal to V in. And what we have done here, just by writing VD is equal to V in, at the same time we have taken these two on left hand side because we want to keep only exponential term on the right hand side and all other terms on left hand side. Therefore, as soon as we written VD equal to V in, at that time only we shifted this RF and IS on left hand side. So here it is a multiplication and here you will get divided. So now exponential term on left hand side and all other terms on left hand side. So in this way now, here only in this equation, Vout is antilog of V in, because here exponential term is antilog. But now suppose you want to say that no, we want that key output voltage Vout is antilog of V in. Like that if you want, then two to three steps are more only. So we'll proceed for that. So after deriving this, now what you do it here, let us take the exponential term on the right hand side and all other terms on left hand side. And here, after this, you take the natural log on the left hand side and natural log on the right hand side. What do you mean by natural log? Natural log means log to the base e, because you want the equation such that V out is equal to, or V out is proportional to antilog of V in. V out is equal to, or V out is proportional to antilog of V in. Then after rearranging the exponential term on right hand side and all other terms on left hand side, what you do, you take the natural log, means log to the base e on both sides, and that is what written over here. See, or let us prove that by taking the natural log of this equation, that is log to the base e on both sides. So log to the base e of what? V out upon Rf into Rs. So in this equation on left hand side is V out upon Rf into Is, and on the right hand side minus sign is there, log to the base e of e raised to V in divided by eta into V2. So here on the right hand side minus sign is there, and e raised to V in divided by eta into V2. We have to take log to the base e of e raised to. So in this way, this equation will be there. And now again, same thing we are repeating using log to the base e of e raised to x. So this x will come over here before log. This will come over here before log. And then what remains? X into log to the base e of e. And you know log to the base e of e is 1. Therefore, equation will be simple. Your ex will remain here only. So in this way here, we use this logic first of all to take this e raised to x something. X means V in divided by eta. On the left hand side means before log. Okay, so that will do. So left hand side will keep it like this only, and that logic if you use, which logic? Log to the base e of e raised to x, x will come here before log. So here this term will take it, x. What is x? V in eta into V2. So minus sign is as it is, so this term come here. And now what should be here? Here should be log to the base e of e here, but we have not written that because log to the base e of e is 1. And in this way we got succeeded in simplifying this particular equation in terms of log to the base e. Now our target is, we want to prove output voltage is proportional to antilog of V in. So now let us take the antilog on left both sides to this equation. Let us take antilog on both sides to this equation. So when you take the antilog of both sides to this equation, then your job is very simple now. Antilog of log to the base e, and antilog and log will get cancelled in the next step. And here on the right hand side minus sign is as it is, antilog of this particular x parameter, that is V in divided by eta into Vt. Now antilog and log get cancelled, therefore V out is equal to, this V out equal to Rf and Is, which is divided by here will get multiplied on the right hand side. So minus Rf into Is antilog of into bracket V in eta into Vt, V in divided by eta into Vt. And this is the final equation, which only I have written into the what? A square bracket blue. And this equation will prove that all the constants are there. So constant will be converted into proportionality constant, and therefore you can write V out is equal to, or V out is proportional, directly proportional, proportionality constant. All the constants will come under proportionality constant. So V out is directly proportional to anti-log of V in. And this is the derivation for your log as, transdiode used as anti-log. So anti-log by using transdiode and operational amplifier. Now we have a time, therefore I am proceeding to the next part immediately without wasting the time, and you are just requested to wait for getting the another slide. And as soon as I get the another slide, yes, I got it. So here next topic is our on-off controller using operational amplifier. On-off controller using operational amplifier. So this on-off controller is also called as two-position controller. So only two decisions are taken. Either the AC main switch is turned on or the AC main switch is turned off. Only two decisions are taken. That's why it is called two-position controller. And it is basically used to control the temperature less than 250 degrees centigrade. It is not advisable for controlling high temperatures in furnaces and like that. There are different methods, that is called your PID method, proportional integral derivative control method. So this is on-off control method. So here we are going to study on-off control method. It is one of the application of the op-amp. It is one of the application of the op-amp. So I will go in a very systematic manner to understand this circuit. Before going to the circuit, I have divided the on-off controller circuit into 4 different blocks. So that 4 different blocks are, namely, in this circuit, number 1, relay is used. And what is relay? Relay is electromagnetic switch. So the first block is relay. Number 2, transistor is used as a relay driver. Transistor is used as a relay driver. Number 3, op-amp is used as a comparator. Op-amp is used as a comparator, and therefore this is said application of the op-amp. And number 4, temperature sensors and signal conditioner circuit. Number 4 is temperature sensor and signal conditioner circuit. So I am going to explain each block in detail, and therefore thereafter we are combining all these 4 blocks, and there will be the fabrication of on-off controller circuit by using op-amp. So let us start from the basic part of the relay. Relay is nothing but electromagnetic switch. Relay is nothing but electromagnetic switch. So physically relay looks like this. Physically relay looks like this. In the market it is available. So here there are 5 terminals. You can see 1, 2, 3, 4 and 5. So what are these 5 terminals in the relay? So on the right hand side you observe the diagram. You will get why there are 5 terminals. So you can see here there is a relay coil. There is a relay coil which is having 2 terminals. Terminal number 1 and 2, you can say. So where is that relay coil out of these 5 terminals? I will explain you. And there are 3 more terminals. Out of that 3 terminals, one is called normally closed terminal, NC. Normally closed terminal, NC, and another is called normally open terminal, NO. And there is one terminal which is common, and this is also called as pole. This is also called as pole. So you remember one thing, there is one logic to remember. Wherever you find out 3 terminals in one line, you can say, or little bit center terminal is away from these 2 terminal. Wherever you find 3 terminals, in that 3 terminal, here you will get 2 terminal. So wherever you find 3 terminal, in that 3 terminal, last 2 terminals are the terminals of relay coil. So wherever you find 3 terminal, in that last 2 terminals are the terminals of relay coil. And this center terminal is called your common terminal, and that is also called as pole. Then out of these 2 terminal, one of them is normally closed and one of them is normally open. So how to identify which is normally closed and normally open? It is also very simple. Take a multimeter DMM, put into the continuity range. So when you short circuit 2 probes of the multimeter in continuity range, it will give the buzzer. So connect one terminal here and one terminal here. If the buzzer glows, then this is normally closed because this is short circuited. And if the buzzer doesn't close, then this will be normally open. And then if you come here, you will get the buzzer is glowing. Okay, so like that. So this diagram I have simplified in a different manner. So like that. So our relay is nothing but 2 terminals for the relay coil. 2 terminals for the relay coil. There is one center terminal which is called common or pole, and there is one terminal which is called NC, means normally closed. So pole is normally closed to that terminal, that's why it is called normally closed, and this is normally open. Now why it is called electromagnetic switch? Because normally relay is operated on 12-volt DC power supply. Relay is operated on 12-volt DC power supply, but remember, relay is used to connect or disconnect. Relay is used to connect or disconnect the AC mains 230 volt. Relay is used to connect or disconnect the AC mains 230 volt to the instrument. Actually, relay is operated on 12 volt DC, but it controls whether the 230 volt AC should get applied to that instrument or should not get applied. So that you are understanding in the next part only. So here, how to throw the pole, means here this switch, to the NO. So you have to magnetize the relay coil. So under this condition, when you don't pass the current through the relay coil remains in normally closed condition. The relay coil means pole remains in normally closed condition. Now see, we have taken a relay, we have taken a battery of 12 volt, and we connected the battery to the relay coil. So battery is always connected to the relay coil. And when you connect the battery of 12 volt to the relay coil, you observe here there is a red mark and dot dot dot. So what is this? This is a magnetic field. So when you pass the DC current through the coil, a steady magnetic field is developed in the relay coil. And due to this magnetic field, this switch, which is called single pole double throw. So this is one pole and there are two throws. One throw is to normally close and another throw is to normally open. So single pole double throw, SPDT it is called. So here when the relay coil gets magnetized, this switch automatically gets connected to the upper terminal, and then therefore this which was normally open, it becomes closed, and which was closed, it becomes open. So this is the operation of the relay. Now how to get relay coil magnetized? It is very simple. Connect the 12 volt of the battery. But now in the control system, we are not going to connect the battery directly to the relay. We are connecting the battery through a relay driver. So first of all, I hope you understood the relay. So it is written here. Relay is electromagnetic switch, and it consists single pole double throw switch. It operates on magnetic field developed in relay coil. It has five terminals. One terminal is upper terminal of relay coil, lower terminal of relay coil. Two terminals. Pole or common is a one terminal. NC is one terminal. NO is one terminal. So it has five terminals, and it operates on 12 volt DC. Now here the description is given. When current is not passing through relay coil, at that time the pole, that is a common, it is also called, is connected to normally closed terminal. So when current is not passing, left hand side, no current is passing, we have taken simply relay. Pole is normally connected to, yes, normally closed terminal. So pole is connected to normally closed terminal, and when current is passed through the relay coil at that time, and when current is passed, actually it should be, and when the current is passed through the relay coil, at that time relay coil gets magnetized. So we have made the connection, and when the current is passed through the relay coil, at that time, due to magnetic field, single pole double throw switch operates, and pole gets connected to normally open terminal, and pole gets connected to normally open terminal. So here see, this way. Therefore normally open terminal becomes normally closed, and normally closed which was there, that becomes normally open. And this will happen if and only if relay coil gets magnetized. If and only if the relay coil gets magnetized, means current passes through the relay coil. Otherwise it remains in normally closed condition only, means pole gets connected to the NC. And this is the simple operation. Now second part is your what? Transistor as a relay driver. So as I told you, we are not connecting directly the 12 volt battery to the relay. We are connecting through the transistor. Now see, it's very simple now. We'll take the plus VCC supply of how much volt? 12 volt, because relay operates on 12 volt. That much magnetic field should get developed. Therefore it is a 12 volt. If you connect the 5 volt, this terminal will not be thrown on that side, because that much magnetic field will not get developed. So here 12 volt supply is there plus VCC, and here it is a ground, means that battery which I have shown over here, in this case plus here and minus here, the battery's plus is plus VCC, this, and minus is this ground. Now what we are doing here, see, we have used the transistor, and transistor, all of you know, it is a transfer of resistance in between 0 to infinity. But we are operating transistor now in only two position. Number one, open switch position, and another is closed switch position. So transistor you take, connect the collector of transistor to one terminal of relay coil. Another terminal of relay coil is connected to plus VCC. Now this ground is here. All of you know very well, if the transistor is open switch, no current will flow through relay coil. Because circuit is disconnected by the transistor, which is behaving as an open switch. Now why the transistor is open switch? Because its base voltage is low voltage. And here this is an NPN transistor. If it is having a base voltage as a low voltage, it will behave as open switch. And look at this diagram, no magnetic field is shown here. Magnetic field is not developed. Therefore here pole gets connected to the normally closed terminal. closed terminal. Now let us proceed ahead. Same relay coil will take plus VCC of 12 volt is applied, but now the transistor's base voltage we have connected to high voltage. Transistor's base voltage we have connected to high voltage, therefore transistor behaves as a closed switch. Transistor behaves as a closed switch, and now from plus VCC current will start flowing through relay coil through transistor as a closed switch, and it goes to ground. And in this way the path is completed now, and that's why transistor is called as relay driver. Transistor is called as relay driver. It drives the current through the relay coil when it is closed switch. When it is closed switch, and it does not drives or passes the current through relay coil when it is open switch, which I have seen earlier. Now, because of the closed switch position of the transistor, current passes through relay coil and magnetic field is developed. See here red. And this magnetic field throws the switch S from normally closed terminal which was there to normally open terminal. Therefore, normally open will become normally closed, and normally closed will become normally open. So this is so simple action of the relay. Number one, relay as an electromagnetic switch. Magnetic field developed controls the what? NC and NO position. And transistor is a relay driver. This is the second part. Now third part, op-amp as a comparator. So in this circuit of on-off controller by using op-amp plays very important role, and it is used as a comparator. So now in this circuit, we are using op-amp LM324 because we want output voltage of this op-amp as a 5 volt, because normal op-amp 741 output voltage will be HVL means plus 12 volt 741, and LVL will be minus 12. So 12 volt if we apply to this transistor as a high voltage, transistor may get damaged. Therefore, we want only 5 voltage of the base volt. Therefore, we are using the op-amp which is called as what? Yes, this op-amp is LM324. It works on single power supply. See here, only plus 5 volt and ground. Here there is a ground. And op-amp's operation you know very well. There are two pins, namely marked by the minus sign inverting pin and marked by the plus sign non-inverting pin. So this op-amp is working on single power supply of plus 5 volt. Now all of you know very well, when the voltage at positive pin, that is non-inverting input pin is higher, at that time the output becomes high voltage level. At that time the output becomes high voltage level, that is output will be equal to 5 volt. And here see it is written vice versa, whenever voltage at inverting pin means minus pin is greater than voltage at non-inverting pin. So here when if voltage is greater, here arrow is marked, if this voltage is greater or higher on this pin as compared to that pin, then the output will become low voltage level. And here our low voltage means what? 0 volt, not minus, because op-amp is used in single power supply. And here it is written that output will be 0 volt or plus 5 volt depending on which input pin has higher voltage. Output will be 0 volt or plus 5 volt depending on which input pin has higher voltage. And this way it is work as a comparator. If the voltage at positive pin, non-inverting pin is greater than inverting pin, output will be plus 5 volt. And if the voltage at inverting pin means minus pin is greater than non-inverting, output will be 0 volt. So this is the op-amp as a comparator, third block. And fourth block is called your temperature sensor and signal conditioner. Temperature sensor and signal conditioner. So what is a temperature sensor? It senses the temperature. Conventionally we are using, or traditionally we are using, thermometer as a temperature sensor. What is a thermometer? Thermometer consists of mercury, Hg, and mercury's property is what? The volume of the mercury increases proportional to the temperature surrounding to it. And this is a very traditional instrument used as temperature sensor, thermometer, which consists mercury, Hg. And property of mercury is what? Its volume increases. Therefore, you see when you hold the thermometer, the capillary which is present inside the rod of thermometer, in that Hg is there. So Hg rises. So Hg what? Goes in upward direction. And that is one traditional instrument. But nowadays very advanced technology is there, and very sophisticated or non-contact type temperature measurement is also there. So in this COVID-19 pandemic situation, this is more popular. Okay, let us come to this block. Now this is our 4 square block, which is called heating system. And in this heating system, this is a heater. This is a heater or heating coil, which is connected to the live and neutral, and this chamber's temperature goes on increasing. Now this temperature is sensed by the various temperature sensors. We'll come to that. Number one, you can use as a thermocouple. Number two, you can RTDs, resistance temperature detector. RTDs means resistance temperature detector, which are made from metals only. Then number third, you can use LM35. Number four, you can use AD590, and various temperature sensors are used. So output of temperature sensor, this is a temperature sensor. So output of temperature sensor is given to signal conditioner. Signal conditioner is very important, because signal conditioner can amplify the output of temperature sensor if it is very low, or give a proper shape. So that is a signal conditioner. So temperature sensor output is given to a signal conditioner, and signal conditioner gives you the output voltage which is changing with the change in temperature. Output voltage which is changing with the change in temperature. Therefore, output of signal conditioner is always expressed as, for example, 10 millivolt per degree centigrade. 10 millivolt per degree centigrade, or it may be 5 millivolt per degree centigrade, or it may be 25 millivolt per degree centigrade. Means what? Means this output voltage will go on increasing by 10 millivolt if the temperature increases by 1 degree centigrade. This output voltage will go on increasing by 10 millivolt if the temperature increases by 1 degree centigrade. So this is a per degree centigrade, that's why written. Now for this example, as it is a 10 millivolt per degree centigrade, suppose the room temperature is 30 degree centigrade, then as the rate is 10 millivolt per degree centigrade, at room temperature 30 degree centigrade, the output will be 300 millivolt. And in this way, this is the last block in our on-off controller by using operational amplifier. Now we'll combine all that blocks and come to the circuit diagram of on-off controller using op-amp. So see here, there is a relay coil, normally open, normally closed, and in this way this relay coil is connected to plus 12 volt supply. The relay driver is there, transistor may work as open switch, or transistor may work as closed switch. If the base voltage is high voltage, it will work as a closed switch, and if the base voltage is low voltage, it will work as a open switch. Now output of comparator, which is high voltage or low voltage. Here which comparator? LM324, working on 5 volt power supply. Output of comparator, it is high voltage or low voltage, is given to the base of transistor. Therefore sometime transistor behaves as open switch, sometime as a closed switch, and it drives the relay, means current will pass through the relay coil or will not pass. Now what is this comparator? As we told you, look at here. Minus terminal means inverting terminal is connected to reference voltage of 700 millivolt with the help of battery, variable battery. So if this is 700 millivolt, and at room temperature, say this output of signal conditioner, which I have studied 1 minute before, signal conditioner output is, suppose at room temperature, that is at 30 degrees centigrade, is 300 millivolt. So this non-inverting input pin is at 300 millivolt. Inverting input pin is at 700 millivolt. So which voltage is greater? Inverting voltage is greater than non-inverting. And op-amp will compare these two voltages, and now result will generated as low voltage. As what? Low voltage, because we have already explained you this. So when this voltage is low voltage, in the beginning transistor behaves as open switch. Therefore this is written over here, and then close switch. So in the beginning transistor behaves as open switch, and when transistor is behaving in the beginning as open switch, at that time relay coil will not get magnetized, because current will not pass through the relay coil, and therefore pole is connected to the normally closed terminal. Pole is connected to the normally closed terminal, so pole is also called as common. Now look at the heater. This is the heating system. We are measuring the temperature of this chamber with the help of temperature sensor. Temperature sensor's output, we are giving it to the signal. Okay, let us come back again to the topic because of some problem in the software. So here, as I just told you, the heating system consists of a heater which is connected. See, the heater is having two terminal which is connected to the AC mains 230 voltage. So one terminal of the heater is directly connected to the neutral. One terminal of the heater is directly connected to the neutral and another terminal of the heater which is connected to the normally closed terminal. Another terminal of the heater which is connected to the normally closed terminal and live terminal of the AC mains voltage 230 volt and live terminal of AC mains voltage 230 volt is connected to the pole. In this way here in the beginning, as explained earlier, when transistor is a open switch, relay coil is not magnetized and pole is connected to the normally closed terminal. Therefore, as soon as we turn on the power supply, live terminal gets connected through the normally closed terminal to the heater coil and neutral is already there. Therefore, heating system will start or heating process will start. Now when heating process starts at room temperature say 30 degrees centigrade, the output of signal conditioner is 300 millivolt, reference voltage is 700 millivolt, output of op amp is in LVL. Therefore, this is behaving, transistor is behaving as an open switch and relay coil is not magnetized. So relay remains in normally closed condition and AC mains 230 volt is applied directly to the coil, heating coil. And in this way here, from room temperature onwards, 30 degrees centigrade onwards, the heating process starts. The heating process, when it starts, the temperature of this particular square box, that is chamber, goes on increasing 35 degrees centigrade, 40 degrees centigrade, 50 degrees centigrade, and you have choose the reference point as a 700 millivolt. Therefore, this reference point 700 millivolt is also called as set point. Means you have set the point at 70 degrees centigrade because when this system's temperature or this heater's temperature here chamber's temperature will just cross 70 degrees centigrade, say 71 degrees centigrade. At 71 degrees centigrade, this output will not be 300 millivolt but it will be 710 millivolt because the rate of change of output voltage is 10 millivolt per degree centigrade, and when you talk about 71 degree centigrade, so this output will be 710 millivolt. In this way here, if you compare the inputs at 71 degree centigrade of op amp, lower terminal, positive terminal, non-inverting terminal will be at 710 millivolt. Upper terminal is fixed 700 millivolt. So this voltage at non-inverting, that is positive terminal, becomes greater than inverting and output of op amp will be thrown in high voltage level. And how much high voltage? It is plus 5 volt. Therefore, transistor will behave now as a closed switch and relay coil gets magnetized and relay coil gets magnetized, and as soon as relay coil gets magnetized, your pole will get connected to NO and therefore NO becomes NC, and this terminal of the pole NO, you see it is not connected anywhere. So as soon as pole is thrown to that NO position, so that becomes NC and NC becomes NO. So here AC mains live voltage to 30 volt now gets disconnected because this will be thrown on that side and live terminal will not get applied to the heater only, and power supply of AC mains 230 volt will get disconnected from heater, and in this way as soon as the power supply of 230 volt is disconnected from the heater, the heating in this chamber will stop. The heating in this chamber will stop and temperature which has gone just 71 degrees centigrade or above 71 degrees centigrade will start decreasing. So in this way, first of all, the 230 volt supply is on through the normally closed and then 230 volt supply is off through the same pole only because this will be thrown on that side and AC mains 230 volt is disconnected. So when it is disconnected, temperature starts decreasing and when temperature starts decreasing, say suppose from 72 or 71 degrees centigrade, then it will come down below 70 degrees centigrade, and suppose when it is coming down below 71 degrees centigrade, say 69 degrees centigrade, then at 69 degrees centigrade this output will be 690 millivolt. At 69 degrees centigrade this output will be 690 millivolt, and now again op amp compares these two, observes that this is 690 millivolt, that is 700 millivolt. So output of op amp is now again thrown into the low voltage level, and relay coil transistor will behave as an open switch, and relay coil which was magnetized now will get demagnetized through this diode, and that is called freewheeling diode. So that magnetic field will be killed and current will not pass through the relay coil because transistor is now open switch. And in this way, when the current is not passing, then again our original position will come, that is pole will get connected to the lower terminal, that is called your normally closed, and again 230-volt power supply will get applied to the heater coil through the normally closed switch. And when this live is getting connected to the heater coil, again the temperature which is decreased to 69 degrees centigrade or 68 degrees centigrade, then again the heating process will start, and in this way again the temperature will go to the 70 degrees centigrade and above 70 degrees centigrade, that is 71, and again the comparison will be done. And in this way, in this process, on and off action will be done for applying the AC mains voltage of 230 volt to the heater coil, and in this way the temperature is maintained approximately 71 degrees centigrade and 69 degrees centigrade in that range, and therefore in this way here it works as on off controller. So see the description here now, as shown in diagram below, means above. At room temperature 30 degrees centigrade, the output of signal conditioner circuit is 300 millivolt, and reference voltage applied to inverting terminal of op amp is 700 millivolt. Therefore, the output of operational amplifier is in low voltage level, that is 0 initially, and transistor does not conduct, relay coil is not magnetized, and pole is connected to the normally closed. Terminal. Therefore, AC voltage of 230 volt AC gets connected to the heating coil. So that is what we have explained you. Transistor open switch, pole is normally closed, live terminal goes through the NC to the heating coil. Heating process starts, and when temperature increases and goes to 71 degrees centigrade, at that time output of signal conditioner circuit is 710 millivolt. Therefore, the voltage at non-inverting terminal of op amp becomes greater than inverting terminal of op amp, and output of op amp is high voltage, that is 5 volt. So in this way, at 71 degrees centigrade, this is 710 millivolt, this is 700 millivolts. So output of amp will be high voltage. Transistor will behave as a closed switch now. High voltage means 5 volt. So it is given over here 5 volt, and transistor conducts, relay coil gets magnetized, and pole of single pole double throw switch. Relay coil gets magnetized, and pole of single pole double throw switch gets connected to the upper NO terminal. Pole of single pole double throw switch gets connected to normally open terminal, that is upper. Therefore, live terminal of 230 volt AC voltage gets disconnected from heating coil, and heating process stops, and temperature is controlled. So in this way here, by using proper temperature sensor and signal conditioner circuit, the rate of change of output voltage of signal conditioner per degree centigrade can be controlled. So different circuits are used, signal conditioner and temperature sensors, and that can be controlled. For RTDs, now what are the signal conditioners here? For RTDs means resistance temperature detector, which is manufactured by using metals only, and therefore temperature coefficient of RTD is NTP. Means what? Normally it is, PTC. positive temperature coefficient. Why RTDs are having a positive temperature coefficient? Because they are made from the metal, and when temperature surrounding to the metal increases, the resistance of the metal also increases. So RTDs are having positive temperature coefficient PTC. Semiconductors are having NTC, negative temperature coefficient. So RTDs signal conditioners such as bridge circuit is used, thermocouple is used, signal conditioner is instrumentation amplifier is used, and for LM35 operational amplifier as a unity gain amplifier is used as a signal conditioner. So here temperature sensor and their signal conditioner names are given, and temperature sensors such as thermocouple, RTDs, AD590, LM35 can be used. The best example of RTD's worst example is PT100. PT means platinum. 100 why? Because at 0 degree centigrade, a standard piece of platinum metal shows 100 ohm resistance. At 0 degree centigrade, standard piece means size of platinum material shows 100 ohm resistance. That's why it is said PT100, and PT100 is one of the best example of RTDs. Platinum is a metal, and therefore when you hit the platinum, as it is a metal, its resistance increases. Therefore RTDs are having positive temperature coefficient, and in this way this is on off controller. And thank you for very much for watching the slide. So there was a little bit inconvenient in the this diagram. Thank you very much.